Okay, so we're going to be doing the ellipse today. So we've gone over the circle and we've gone over the parabola. So the next step is the ellipse. I find the ellipse a little bit easier than the parabola, only because the having the center and then the vertices and co-vertices just being that distance from the center makes it a lot easier. Okay. Now the ellipse itself is a really important shape. Okay. When we talk about our solar system, planets generally form an elliptical orbit around the sun. Okay. And it has some interesting acoustic applications. For instance, in the Capitol building is got an elliptical shape, and you can see the phenomenon of the foci. Okay, because if you're standing on one end of the room in the focal point, and then someone else is standing in the other side, you can actually hear their conversation as if they were standing right next to you, even though they're 40 feet away. This acoustic phenomenon we actually here in Houston at Discovery Green. There are actually these two concrete bowls that have this chair, and you sit in the chair, and there's another one like 40 yards away, like this little bench, and you sit in it and you can talk, and the sound waves will actually bounce off the concrete structure behind you. It focuses them all the way to the other side, and the person sitting in the other chair 40 yards away can hear you. It is the craziest thing you'll ever experience. Okay, so this acoustic phenomenon is huge, and you see it in a couple of places. There's another one that we'll talk about in a minute in the cathedral. So what is an ellipse? Just like a parabola, it's a set of all points that are the same distance from the focus and the directrix. A ellipse is all the points where the sum of the distances from two fixed points called our foci, or some people will say foci. Okay, we don't say focuses. So it's those same points. So basically what we're saying is, if you have these two focal points right here and here, this distance from here to here and this distance from here to here is constant no matter where the point is. So if I pick another point, if I say this point here, P2, this distance from here to here and here to here has to be the same. Matter of fact, that's how you draw an ellipse. If you want to draw a perfect ellipse, what you do is you get a piece of string and some tape, and you tape down the two ends. Those are your focus points, here and here. And then you take your pencil and you make the string tight and you start drawing it. Okay? It'll actually, when you do it this way, it'll draw the top half. And then you pick up your pen and you put it down the other way and it'll draw the bottom half. And that's how you draw a perfect ellipse, by using its definition. It's actually pretty cool. You should try it out. Okay? So, let's talk about the characteristics. Another thing that we use the ellipse for is we actually use it in medicine. There's a medical procedure where they use an elliptical tank, and people with kidney stones or gallstones or anything like that, they actually put them in this tank of water, and as the waves, the concussive waves that it creates travels through the water, it doesn't lose momentum. So what ends up happening is they put people in these tanks, and it actually breaks up the solid stone so that they can pass them without having to do surgery. Okay, but they put the device in the one focal point, and they put the patient in the other. And since we're 70% water, the waves, the concussive waves, the sound waves will pass through us without a problem. But those crystalline rocks that are formed in the kidney will actually break apart. Okay, it's actually really cool. And also in St. Paul's Cathedral in London, there's a elliptical waiting area where you can actually see them. And there's also dead zones where you can't hear anything. Basically, those zones where sound leaves that spot but never comes back in. So you could be walking through and hearing your footsteps, and all of a sudden they disappear. Like you can't hear anything. And then you leave it and you start hearing stuff again. It's the creepiest thing you'll ever see. Or hear, technically. All right. So let's talk about the characteristics of these ellipses. General rules. X and Y both have to be squared. Okay, so if you look at your formula chart, X and Y both have to be squared. The equation's always equal to 1. We're talking about its its normal conic form. Okay, sometimes we have to get it to fit this equation. The equation is always a positive. It's always x squared plus y squared. A squared is always the biggest denominator. So when we talk about the formulas, a squared is always the biggest number. Okay? This is the equation to find c. C has to do with the distance to the focal points. And it looks sort of like Pythagorean theorem, but instead of a squared plus b squared, it's a squared minus b squared. C is the distance from the center to each foci on the major axis. And the center is in the middle of everything, hence the name center. The center is in the middle of the vertices, the co-vertices, and the foci. Okay? Now, A is the distance from the center to each vertex on the major axis. Okay? So if you start at the center and you go to the vertex, you're going a distance of A. B is the distance from the center to the co-vertices. Okay? So vertices has to do with the longer side of an ellipse, and co-vertices have to do with the shorter side of the ellipse. Okay, that's kind of how it works. Okay. Major axis has a length of 2a. Minor axis has a length of 2b. That's kind of self-explanatory, because if you're going from one vertices to the other vertices, its distance is 2a. Eccentricity, that's just a fancy way of saying how much the ellipse looks like a circle. Okay? And the closer C and A get, and the E gets closer to 1, the closer it looks like being a circle. Now, an ellipse and a circle, it's the whole rectangle and square thing. A circle is technically an ellipse, but not all ellipses are circles. Okay? A circle is just an ellipse where the major axis and the minor axis are the same length. Okay, just like a square is technically a rectangle, but not all rectangles are squares. Okay, that same kind of idea. For my students, your code for today is 3LL1PS3. 3LL1PS3. Now, a horizontal ellipse has the following characteristics. The vertices are plus or minus a 0, co-vertices are 0, plus or minus b, and the foci are plus or minus c 0. Okay, so this is my ellipse, x squared over 16 plus y squared over 9 equals 1. Now what you need to notice first and foremost is that this is a horizontally major ellipse. Now, this is where it becomes super simple. It's horizontally major, and how do I know it's horizontally major? Is because the bigger number is my a squared, right? So a squared is 16, but my bigger number is under my x value. X values are my horizontal values. So if the bigger number's under the x, it's horizontally major. If it's bigger numbers under the y, it's vertically major. So that's the easiest way to tell if an ellipse is vertical or horizontal. Is the bigger denominator, bigger number, under the x, or is it under the y? Okay. Now, if your center is not at the center, or at the origin, then we have our h and our k added in. Okay, so if you have h and k, like this one, again, it's horizontally major because a squared is under my x. But now my center's at a different spot, and that's our vertical and horizontal shift, h and k. Okay? Now, a vertically major ellipse looks like this. Basically, when we say vertically major versus horizontally major, we're talking about which side is longer. Is it longer up and down, or is it longer left and right? So as you can see, this one is vertically major because it's longer up and down than it is left and right. And if you notice that a squared is under my y, or my bigger number is under my y value this time. So because this number is bigger right here, it's bigger here in this direction. So for instance, this distance right here is 9, because the distance from the center to my vertices is a. this is a squared, so the square root of 81 equals 9. This, the square root of 9, is 3. And this distance from here to here is 3. So basically we're going this distance in my x direction and this distance in my y direction. That's how these major and minor axes work, the vertices and the co-vertices. Okay? It becomes really, really simple. Okay? And again, if you have an ellipse that's vertically major and it's going not at the origin, then we just have to add h and k in. And it's the same equation. And again, you know that this is vertically major because the a is with the y. Now notice it doesn't matter if my ellipse is vertically major or horizontally major, x squared always comes first. So in both, x squared comes first and y squared comes second. A and b move spots to tell me horizontal or major, which is different in our hyperbola. And when we go over that, we'll talk about how you can tell if those are vertically major or horizontally major. Okay? But basically, we're just following our formula charts. Okay?